In late summer 2020, the western United States erupted. Millions of acres of forest burned, towns were swallowed by heavy smoke, and thousands of people were forced to flee down highways for their lives. To those watching from the ground, the disaster seemed to materialize out of nowhere. One day the air was dry, and the next, entire mountain ranges were walls of fire. It felt like an overnight, violent ambush by nature. But 700 kilometers straight up, a NASA satellite had actually been watching this specific catastrophe quietly assemble itself weeks before the first spark caught. From orbit, the satellite detected an invisible signal. Vast stretches of forest along the coast had suddenly stopped their photosynthesis, their biological systems entering a state of severe, measurable stress long before the first tree ignited. This exposes a fatal flaw in how we usually track the environment. By the time our ground weather stations or our own eyes register cracked soil and dead leaves, the damage is already done. If we want to protect our food supplies and cities, we need a chemical early warning system that watches the entire planet in real time. Back in the 1990s and early 2000s, carbon dioxide levels in the atmosphere were breaking historical records. Climate scientists knew the Earth was warming, but they lacked a reliable global system to track exactly where carbon was moving. Ground sensors were strictly localized, leaving the global picture incomplete. NASA's answer was the Orbiting Carbon Observatory, or OCO, but the initial attempt ended in disaster. In 2009, the protective fairing on the OCO-1 rocket failed to separate, dragging the entire multi-million-dollar mission down into the Pacific Ocean. They refused to scrap the project. The technology was too crucial. 5 years later, NASA successfully placed OCO-2 into orbit. They even used spare hardware from the first two builds to create OCO-3, attaching it directly to the exterior of the International Space Station. To read the atmosphere's chemistry from space, these satellites rely on a very precise physics engine. It starts with sunlight striking the surface of the Earth and bouncing back up into the void. As that reflected light travels back through the atmosphere, gases interfere with the beam. Carbon dioxide, for instance, naturally absorbs very specific, exact wavelengths of infrared light. When that light finally reaches the satellite, highly sensitive spectrometers break the beam apart into thousands of tiny individual bands. By looking at this exact graph and spotting which precise slices of infrared light are missing, computers can calculate the concentration of CO2 molecules in the air down to a single part per million. The engineering worked perfectly. Humanity finally had a high-definition, continuously updating map of the planet's dead carbon gas. But shortly after the system powered on, researchers noticed something strange. Their pristine carbon data was being contaminated by faint, unexpected flashes of infrared light coming from the surface. What they were seeing is a phenomenon called solar-induced fluorescence, or SIF. When a plant's chlorophyll absorbs sunlight to generate food, a tiny, invisible fraction of that solar energy leaks back out into the air as a very weak infrared glow. The OCO sensors were so incredibly sensitive, they were picking up this microscopic glow all the way from orbit. Because healthy, active plants glow brighter, the satellite was effectively measuring exactly how efficiently the world's forests and crops were photosynthesizing at any given moment. With this data, we no longer have to wait weeks for a field of corn to turn brown and wither. We can see those plants entering biological stress the second a heat wave hits or the soil moisture drops. By pure accident, a machine engineered to track dead greenhouse gases had evolved. It became Earth's first real-time biological heartbeat monitor, giving us a live feed of the entire planet actively breathing. The practical applications of this discovery are significant. By tracking that biological heartbeat, scientists can predict devastating flash droughts weeks before they ruin harvests. This foresight allows farmers to adjust early, stabilizing global food supplies and protecting agricultural economies from sudden collapse. The data also serves a major geopolitical purpose. Because the satellite tracks localized carbon spikes with extreme sensitivity, analysts can uncover expansive industrial projects or hidden power plants that a country might be trying to keep off the books. And it acts as a diagnostic tool for our critical ecosystems. The OCO is currently tracking how rising temperatures are damaging vast carbon sinks like the Amazon rainforest, showing us exactly where these dense jungles are failing to absorb carbon like they used to. Despite providing all of this intelligence at a remarkably low operating cost, this system is now under threat. NASA's proposed budget for 2025 includes plans to permanently shut down both OCO2 and OCO3. Both instruments are still perfectly functional. If left alone, they have enough life in them to keep gathering vital data until at least 2030. Deactivating these instruments destroys a completely irreplaceable 10-year baseline record of Earth's atmosphere. In climate science, long-term continuity is everything. Without that unbroken dataset, any future satellites we launch will have a much harder time calibrating their findings. Right as climate-driven disasters like intense wildfires and flash droughts are peaking in frequency and violence, we are choosing to turn off our most effective early warning system. The ultimate value of space observation isn't looking outward at the stars, it's looking down and securing human survival on the only planet we have.